Tour. Hey everyone, welcome back to the channel. Today, we're diving into one of the greatest detective stories in scientific history, how we figured out what really killed the dinosaurs. For over a century, the disappearance of these magnificent creatures was a huge puzzle. Scientists had all sorts of theories, from massive volcanic eruptions to climate change, and even strange ideas like a global pandemic. But the truth turned out to be far more dramatic and came from outer space. Our story starts in the late 1970s with the father-son team, Luis and Walter Alvarez. Walter, a geologist, was studying a peculiar layer of clay in the rocks near Gubbio, Italy. This clay layer, just a few centimeters thick, marked the boundary between two geological periods: the Cretaceous, when dinosaurs roamed the Earth, and the Paleogene, the era that followed their extinction. This boundary is known as the KPG boundary, and it's found all over the world. Below this layer, you find abundant dinosaur fossils. Above it, there are none. Something dramatic happened right at that moment in Earth's history. Luis Alvarez, a Nobel Prize-winning physicist, suggested they analyze the chemical composition of this strange clay layer. They were looking for a way to measure how long it took for the layer to form. They decided to measure the amount of iridium, a very rare element on Earth's surface, sponody. Most of our planet's iridium sank to the core when the Earth was young and molten. However, iridium is much more common in asteroids and comets. The Alvarez's idea was that a slow, steady rain of cosmic dust would deposit a tiny, predictable amount of iridium over time. By measuring it, they could calculate the time span. But when the results came back, they were absolutely stunned. The clay layer didn't have a little bit of iridium. It had a massive amount. We're talking hundreds of times more than the surrounding rock layers. This wasn't a slow rain of cosmic dust over thousands of years. This was evidence of a sudden cataclysmic event. A single, massive influx of extraterrestrial material. The conclusion was inescapable. A giant asteroid, about 10 kilometers or 6 miles wide, must have smashed into Earth. In 1980, the Alvarez team published their groundbreaking paper, proposing the impact hypothesis. They painted a terrifying picture. An asteroid the size of Mount Everest slams into the planet, releasing energy equivalent to billions of atomic bombs. The impact would have vaporized rock, sending a superheated plume of dust and debris high into the atmosphere. This would have created a global firestorm, incinerating everything in its path. Then, the immense dust cloud would have spread around the globe, blocking out the sun for months, maybe even years. This impact, winter would have been devastating. Without sunlight, plants would die, collapsing the entire food chain. Photosynthesis would stop in the oceans, killing off plankton, the base of the marine ecosystem. Temperatures would plummet. Herbivorous dinosaurs would starve first, followed quickly by the carnivores that preyed on them. Only smaller, more adaptable creatures, perhaps those that could burrow or hibernate, would have a chance of survival. This explained why not just the dinosaurs, but around 75% of all species on Earth vanished at the KPG boundary. Initially, the scientific community was deeply skeptical. It sounded like something out of a science fiction movie, not a serious geological theory. The dominant theory at the time favored massive, prolonged volcanic eruptions, like those that formed the Deccan Traps in India. Proponents of this view argued that volcanic activity could also release dust and change the climate, and it seemed like a more earthly explanation. For the impact hypothesis to be accepted, scientists needed more than just a layer of iridium. They needed to find the murder weapon, the crater. The search for the crater began. Scientists knew it had to be huge, around 150 to 200 kilometers in diameter. But the Earth is a big place, and 66 million years of geological activity can hide a lot. Researchers started looking for other clues associated with a massive impact. They found them. All around the world, the KPG boundary layer also contained shocked quartz. These are quartz crystals with a unique crisscross pattern of fractures that can only be formed under the immense, instantaneous pressure of an asteroid impact. They also found tiny glass-like spheres called tektites, which are essentially melted rock that was flung into the air and solidified as it rained back down. The distribution of this evidence started to point towards a specific area, the Gulf of Mexico and the Caribbean. The ejecta layer was thickest there, suggesting the impact happened nearby. The breakthrough came in the early 1990s. Geologists Alan Hildebrand and Glenn Penfield connected the dots. They had been studying strange gravitational and magnetic anomalies off the coast of Mexico's Yucatán Peninsula. First identified by oil prospectors years earlier, these anomalies formed a near-perfect circular arc, over 180 kilometers wide. This was it. The crater was buried under a kilometer of younger sediments, but its outline was unmistakable. It was named the Chicxulub Crater, after a nearby town. The age of the rocks from the crater matched the KPG boundary perfectly. 66 million years old. The smoking gun had been found. Here was the physical scar left by the asteroid that ended the age of dinosaurs, Bells. The discovery of the Chicxulub Crater was the final piece of the puzzle. It cemented the impact hypothesis as the leading explanation for the mass extinction. Subsequent research has only strengthened the case. Core samples drilled from the crater have given us a minute-per-minute account of the hours and days after the impact. We've found evidence of a colossal tsunami triggered by the impact that swept across ancient coastlines. We've also learned that the area where the asteroid hit was rich in sulfur-bearing rocks. When these were vaporized, they released enormous quantities of sulfur into the atmosphere, creating sulfuric acid aerosols. These were even more effective at blocking sunlight and causing devastating acid rain than the dust alone. So, while volcanic activity in the Deccan Traps may have been stressing the global ecosystem at the time, it was the Chicxulub impact that delivered the final knockout blow. It was a cosmic 1-2 punch that reshaped life on our planet forever. It's an incredible story of scientific deduction, starting with a thin layer of clay and ending with a giant hidden crater. It shows how different fields of science, geology, physics, paleontology, chemistry can come together to solve a deep mystery about our planet's past. The death of the dinosaurs wasn't a slow decline, it was a sudden, violent catastrophe from the sky. And in a strange way, we owe our own existence to it. With the giant dinosaurs gone, the small mammals that survived the apocalypse had a chance to thrive, diversify, and eventually evolve into us. What an amazing journey of discovery! What do you guys think is the most fascinating part of this story? Let me know down in the comments. Thanks so much for watching, and if you enjoyed this journey back in time, don't forget to like, subscribe, and hit that notification bell for more deep dives into the wonders of science. See you in the next video.